In the previous section, we looked at some code that would simulate battery packs having different random characteristics for many possible driving profiles to see how quickly a battery pack could become out of balance. Here I want to quickly show some results of that to give you an idea of what could happen. I ran the code for 100 random battery packs. So the same set of parameters, I randomized the same things. In fact, I think I randomized everything that was possible to randomize when I did these simulations here. So this is kind of a worst case, but I took 100 worst case battery packs off of the production line and simulated each of them to see what would be the dispersion among the results. Each one of these battery packs had 100 cells, which is more or less typical, and I had 180 discharge charge profiles for a number of different scenarios, but I think I present the worst case scenarios here. 180 discharge charge profiles, if I drive the car every day, that's about half a year. What I plot below are some histograms of end of charge SOC. So I've done a full discharge and then a full charge. And then what is the histogram of SOC among these battery packs? And I have all 100 random packs drawn to give an idea of the variation expected if I don't do any balancing after some number of discharge and charge cycles. And I also plot versus cycle number, the minimum and the maximum and the mean state of charge of every battery pack to give an idea of how quickly the state of charge can diverge. This is the worst case scenario. I think everything is randomized. And this is shown for 50 cycles here, not 180, but this is after only 50 cycles, about 50 days driving, maybe 2 months, for fairly reasonable assumed parameters for fairly good cells. This is what we get. We would charge the battery pack every time until the maximum cell hit, I think it was 95% SOC is what we said. But when the maximum cell hits 95 SOC, notice what the worst case cell hits. It hits somewhere around 45% SOC. So we have a 50% dispersion in SOC after only 50 days driving. So about 1% per drive cycle is the added dispersion that you get, at least over 50 drive cycles. That's pretty awful. If that kept on going, this battery pack would be useless before too many more days had elapsed, because I'd have one cell at the lowest SOC and one at the highest SOC, and I couldn't do anything. Now, I've shown you that thing, the two-cell battery pack, a number of times where we said this one was full and this one was empty, and we said, that would never happen in real life. But now we see, using pretty reasonable parameters, it actually could happen in real life unless I do balancing. So balancing is critical. I have to do it. Well, what happens to the spread in SOC versus time? That's what this plot is showing here. The blue horizontal line shows, well, sure enough, after one discharge cycle and one charge cycle, the top SOC is 95%. In fact, after any number of discharge and charge cycles, the top SOC is 95% because that's my stopping criteria for charging. But look what happens to the lowest SOC. The lowest SOC diverges. It diverges rapidly. This is the average SOC, if that means something. The lowest SOC probably means something more. Now you could look at that and say, oh, well, it's the divergence is slowing down. Not that that's too helpful, because I'm pretty close to 10% by 180 days. Remember, 10% was my minimum operating SOC, so I'm pretty much completely useless after 180 days. It's slowing down only because when I'm doing my discharge cycle, I'm discharging until my minimum cell hits that limit. Well, my minimum cell is already almost at that limit, so I discharge very little before I charge again when I'm at these high number of cycles. So there's almost no usable energy out here. Which is very bad. Up here, it's still okay. It seems to be diverging more quickly. In fact, it's not really. It's just I'm getting more use out of the pack. diverging more quickly per cycle number, but not per second of use, if you will. So in this example, if you look at this, I need to be able to balance at least 1% capacity per drive cycle per cell. So you can figure out, well, how long do I have to balance? How much is 1% capacity in amperes? So I have amperes, Q is so many amp hours, and I multiply by 0.01. That's the delta Q I need to be able to do, which is again in amperes. I divide by the number, divide by the time I have to balance, and that gives me a balancing current that I have to be able to support. And can I support that balancing current with a passive balancing scheme and a resistor, or do I have to use an active balancing scheme, is ultimately the decision that you have to make. I believe in this case the battery pack I simulated was a 7.7 amp hour pack, which means I need to balance at about 77 milliamp hours per cell per balancing period, and you want to over-design that, of course. Passive balancing in this case, suppose I have 10 hours to do it. Well, that means that I need to be able to balance at 7.7 milliamps continuously over 10 hours, which is not an awful lot of current. So passive balancing can be fast enough to keep this pack in balance, even though it looks like this is a really awful scenario. It's not really all that bad. Passive balancing, however, is not fast enough if I want to maximize energy or power or to extend life by quick charge transfer. So these are the kind of trade-offs that you'll have to make. The simulation can tell you what the minimum is, but then you have to decide if that's enough to meet all of your objectives. Another thing that was not simulated here was if you drive your vehicle to the airport and you park it for a month while you're out of town, the self-discharge is going to be continuing even while the other modes of dispersion of SOC are not continuing. So more balancing may be needed than predicted by this kind of simple approach. Well, we've reached the end of this chapter on balancing, and I've probably asked more questions that I've answered, but I think that by the end of this chapter we got to see this simulator, and the simulator can answer those questions. And maybe we need to enhance the simulator to add some other effects to it and so forth, but it's an approach that can be used in a design without building a lot of circuitry and a lot of battery packs and testing out a lot of things in real life. We can quickly evaluate what should be a good design and maybe over-design it a little bit so that we can be sure in practice it actually is. So we've discussed in this course so far estimating state of charge and state of health and how to balance, and we said that balancing was more of a control task than an estimation task. And we've done a little bit of talk about power limit estimation in Chapter 1, but we're going to revisit this because the remainder of the course is going to talk about ideas surrounding power limits and how we can improve on the present state of the art in power limits. And this is an estimation thing, it's a prediction thing, it's really a control thing because I'm going to be using my calculation to control how the battery pack is used to make sure that I don't exceed voltage limits, to make sure that I extend the life of the battery pack or whatever my objective happens to be. And that's where we go next.